Now I want to illustrate another example of applying Newton's laws to a situation involving blocks. So we have a block here, 6 kilogram, it's falling down, it's connected with a string to a pulley, and then there's two string going around the pulley. One part of the string is connected to the wall here, and the other part of the string is connected to an 8 kilogram block. We want to find the acceleration of this system, okay? How fast does this accelerate? How fast does this accelerate? This illustrates cases where you have a pulley and then a string is connected to across the pulley, and then the pulley is moving, and then you have another pulley that is not moving, okay? So you could apply this scenario to other kind of situations like this. How do we analyze these? I will do this without friction here. I will assume there's no friction. But if you do include friction, it doesn't change the problem that much, okay? So it just slows this down a little bit more, and then you can include friction without changing the problem a lot, okay? But for now, let's assume that there's no friction here, okay? So how do we analyze this? So we have the weight of this, 6 times 9.8, and then we have a tension here holding this up, T1, okay? We'll call that. So this is accelerating down at an acceleration of A. Okay, then the tension T1 propagates all the way here and pulls on this pulley this way, tension T1. And then the tension in this string is T2. So T2 is pulling on this pulley this way, pulling on this pulley this way, and then T2 is pulling the 8 kilogram block this way. So first we have to determine what is the relationship between T1 and T2. Okay? So if we analyze what is happening to the pulley, we say T1 is this way, okay, minus 2T2, so there's two tensions pulling the pulley back, is equal to the mass of the pulley times the acceleration of the pulley going this way, right? In problems such as these, we usually ignore the mass of the pulley. If we didn't, then the problem would change a little bit, okay? But if we assume the pulleys are negligible, their mass is negligible compared to the mass of the blocks, then this is going to be approximately 0. And therefore what? T1 is going to equal 2T2. So therefore, whatever tension this string has is twice the tension that this string has. Okay? The next thing we have to analyze is, at what rate does this accelerate forward? Is the acceleration of the 8 kilogram block A? Or is it different than A? Do they have the same acceleration? Does the pulley have the same acceleration as the block? Okay? Well, let's think about this a second. If the block moves down, let's say 2 meters, let's analyze what happens. Does this pulley move at all? The answer is no, right? It's standing still. Does this pulley move to the right? Yes, it does, right? It's moving this way. How far does it move? Well, if this goes down 2 meters, okay, we can pretty much agree that this also will move forward 2 meters because the same string is connecting the 6 kilogram block and this pulley, right? So this pulley moved to the right 2 meters also. So it will go like that, 2 meters this way, okay? Now, how far will the 8 kilogram block move? Okay? How far will that move? Will it move 2 meters? Well, in order to analyze it, let's assume something here. Let's give out some numbers. Let's say in the original position, the distance from the wall to where the string is touching the pulley, let's say that distance was 6 meters. It doesn't have to be, but I'm just saying let's assume it was. And then let's say the distance from where the pulley is touching the string here to here, let's say that was 4 meters. Right? And therefore, what would this distance be? Okay, let's erase this. So we're saying this is 6 meters here. This is 4 meters here. And then what would this distance be from the edge of the block to the wall? Well, if this is 6 and this is 4, this would have been 2 meters, right? Okay, so now, when the pulley moved to the right 2 meters, right? What's going to be the situation here? Therefore, the pulley will be in this location, right? This string will go this way, come back. What will this distance be? From here all the way to the wall. Well, 6 plus 2, therefore it's 8 meters, right? The pulley will be here. So what should this distance be? Okay, this is very important here, okay? What should this distance be? Well, remember, we threw out some numbers. We said, let this be 6, let this be 4. That means the length of the string is 10 meters. The string's length can't change, 6 and 4. And then this extra distance was 2 meters, right? But the length of the string was what? 6 and 4, 10 meters. So if this is 8 meters this way, the length of the string this way has to be what? It has to be 2 meters, right? So this is 2 meters here, from here to here. Therefore, where's the block? Right here. Okay, now what's the distance from the front edge of the block to the wall? Okay, well, if this is 8, right? And you're going back 2, and therefore what does this have to be? Well, 8 minus 2 gives you 6 meters, so this distance has to be 6 meters. Notice what happened. The 8 kilograms started out 2 meters to the right of the wall. It ended up 6 meters to the right of the wall. How many meters did the 8 kilogram move? It moved 4 meters, 2 to 6, right? 4 meters. So from here to here was 4 meters. Okay, well, my picture is not very much to scale. It should be longer than this, okay? So therefore the conclusion of this is that no matter how far this moves the same amount, and since the string length is constrained to be constant, the 8 kilogram block moves twice the distance that the 6 kilogram block moves, therefore it has twice the acceleration. And that is our conclusion. If it moves twice the distance, it has twice the acceleration. So, therefore what happens, we can say the 8 kilogram, it is equal to the tension T2 acting on it this way, right? And then it's accelerating at 2A, twice the acceleration of that one. So therefore the equation of it is T2 is equal to MA, its mass is 8, its acceleration is 2A. This is its acceleration, we can call it A prime. So mass of the block times acceleration of the block, and acceleration of the block is twice the acceleration of that block, which we're calling A. So T2 must be equal to 16A. Now what are the equations for this guy? We have 6 times 9.8 minus T1 is equal to 6A. T1 is equal to what? 2T2. So we substitute that. 6 times 9.8, 48, 4, 54, 58.8 minus T1 is equal to 2T2. Okay? And then T2 is equal to what? 16A. So we put that there. 58.8 minus 2 times 16A equals 6A divided by 38. The acceleration A comes out to be 1.547 meters per second squared. So the acceleration of this block will be 1.54, the acceleration of the pulley will be 1.54, and then the acceleration of this block will be twice that. So it'll be that times 2, 3.0947 meters per second squared. Okay? Notice what's going to happen. If the table is very, very long, eventually the block is starting to catch up to this pulley. Okay? So what's going to happen if the table is very long? The block will come touch the pulley, and then probably unwind or something like that, okay? So after that, it will not accelerate. You will hit the pulley and other stuff will happen, right? So it's actually catching up to the pulley. So you can now see how to approach these kinds of things. Two blocks, one accelerating at a different rate than the other, okay? Thank you very much.